Okay, Andy.
All right, thank you. My name is Andy Walls. I'm the CFO of SilverBlock Systems, and today's brief on symbol clock recovery and improved symbol synchronization blocks is basically a growth out of my work to fix a frustration I had with tag propagation through these particular blocks in GNURadio. And as I peeled the onion, I realized there was a few more things that needed to be fixed, and it snowballed from there. So my objective for this brief is to not only introduce the new blocks I've written that are now checked in on master branch, but to educate GNURadio users and developers on how to effectively use these blocks to accomplish the goal of recovering symbols. Okay. So the brief will start out with a quick advertisement about my company. Then I'll go over the theoretical aspects of these particular blocks in symbol synchronization. And then I'll move on to the more practical aspects of how to actually use these things and provide some guidance. And you don't have to digest everything in this brief today. I'm hoping it's up on the website so that it could be used as reference material as well after the conference. So SilverBlock Systems was a small company founded in 2009, literally in my basement. We've moved to better offices since then in Leonardtown, Maryland. We're about a quarter mile from the waterfront, which is nice when you need to get out of the office, clear your head, go stare at the water. We also have an office in Rochester, New York. We build distributed mission computing and display software and license that. We do radar processing algorithms and GPU implementations, experimental comm systems, experimental airborne sensors and systems. We also do some UAV flights and data collection. We have a UAV pilot on the payroll. We're looking to hire 1 or 2 experienced software engineers. C++ is required. US citizenship is required. There's the contact information, contact@silverblocksystems.net. Okay, so symbol synchronization. This is sort of a graphical problem statement here. We want an output sample stream that is synchronized with the center or the optimal sampling point of our data symbols. So here on the left, we have a notionally unsynchronized sample stream coming in, and what we would like is something like on the top left or top right in green is 1 sample per symbol, taken at the center of a sample. Or maybe something more exotic like 3 samples per symbol, again, synchronized, at least one of those 3 samples at the middle of a symbol. So there's 2 broad categories of algorithms to sort of do this. Feed forward or open loop is a block-oriented type of technique to deal with this. You operate a large number of samples or symbols at a time. You can do some really complex stuff. You might apply this for burst mode communications or initial acquisition of synchronization. Feedback or closed loop system is stream oriented. You sort of operate on the immediate incoming sample. It's a tracking mode. It's usually not computationally complex for any one input sample. Good for continuous streams of symbols or after tracking, after you've gotten an initial acquisition. So the algorithm and the implementation sort of impose some requirements on you. You need to do some resampling. These input samples will not be at your optimal sampling instance many of the times, so you need to resample with interpolation. This imposes some bandwidth requirements on your resampling filter. Your symbol, you have to do some sort of symbol clock timing estimation or timing error estimation. You don't know what the symbol clock is. It hasn't been passed to you. You have to look at the sample stream and sort of deduce where it is. So you need to do some signal conditioning before you do this to make it a little easier on the timing error detector. And to really do this effectively, you need offline modeling and simulation and analysis by the designer. It really does take some work to get optimal results. So GNURadio has a couple of these implementations. There's one feed, I'll call it one. It's really sort of half of an implementation of a feed-forward algorithm. The corest block will correlate against a preamble, and if you do it right, it'll give you an estimate of where it thinks the optimal sampling time of one symbol is, and then down the stream you can resynchronize. In a block downstream, you can resynchronize your timing to that open loop marker. GNURadio has basically 4 implementations of a PLL-based feedback algorithm. It had 3. Since I added 1 more, it now has 4. What could be better? All right, so The rest of the talk are really going to focus on this PLL Symbol Synchronizer architecture, so try and keep this block diagram in mind as we go through the rest of the brief. Out in front, you have a match filter to do signal conditioning. When we get to the implementation, there are some smart ways where you can pull that match filter into the interpolating resampler and save yourself some filtering. The interpolating resampler is sort of the nature of this thing is you have multiple samples per symbol coming in, and you want, let's say 1 sample per symbol on the way out. So, the job of the interpolating resampler is to give you that sample right at the center of the symbol. And to guide that resampler, we have a feedback loop. Timing error detector is trying to estimate how far off we are from the symbol center. We have a loop, proportional integral loop filter to smooth out that error signal, and then resampler control to readjust the resampler as we start to converge and track. The timing error detector is really analogous to a PLL phase detector. It estimates the symbol clock error. It's a hidden quantity, so the best we can get is an estimate there. Okay, that's all I'm going to talk about on this slide. So now that we have this this piece parts, this block, we need to sort of analyze how it's going to work. So we need to build a model of these pieces as they're working together. So here we have a model. We're going to model the timing error detector off to the left there as a phase detector with some phase detector gain we'll call K. It outputs an error signal once every symbol. We'll put that error sample through a proportional integral loop filter. The alpha is the proportional gain. The beta is the integral gain. And as a note, what's being accumulated on this integral branch, what I'll call the estimate of the average phase increment, really in the implementation, it turns out to be an estimate of the average symbol period. And then the combined output of the proportional arm and the integral arm gives us our instantaneous phase increment to get to where the next optimal sampling point is. This really in the implementation turns out to be the instantaneous symbol period, so we can get to the next symbol. So now that we have that model, we can write a discrete time difference equation, do some Z transforms, do some algebra, and get to this phase loop transfer function. Use in terms of the proportional and integral gains. There it is. It's got some zeros marked there. It has a couple of poles given by that quadratic solution down there. And the one thing I want to point out is that if you go to critical damping where the poles converge to a double real roots, you have that relationship there on the bottom between the alpha and beta gains and the phase detector gain. Tuning these loops or adjusting these loops in terms of the alpha and beta gains can be a little non-intuitive. So following Tom Rondeau's lead with what he did with his symbol synchronizer block and some of the PLL blocks is we'll put this in terms of a second order control system. So we have the poles of an analog second order control system in the S plane, and we want to map those to the Z plane. So we start out with these poles, S1 and S2, in terms of a damping factor, a natural frequency, which is approximately the one-sided bandwidth of the underdamped control system. And we have omega D, which is the damped frequency of oscillation, which is the ringing you see and the impulse response. We use this transformation Z equals e to the st to take things to the Z plane, and we end up with these poles P1 and P2. And after a good deal of algebra, we come up with the equivalent version of the transfer function you saw on the last slide for the underdamped case, the critically damped case, and the overdamped case. And really the difference between all three of these cases is whether it's cosine 1 or hyperbolic cosine. Don't get too hung up on those. There's one thing I want to point out is that in these expressions you'll see omega n next to a capital T. That T is the clock period we're estimating. Omega n is our proxy sort of for the loop bandwidth. So when we multiply omega n by the T, what we have is a normalized loop bandwidth. So we can sort of, when we're tuning these loops and setting these parameters, we can decouple from the actual clock period and just talk about a normalized loop bandwidth. So once we can sort of have knobs to say, I'd like to change the loop bandwidth to this and the damping factor to that, we have these equations here to map those to the alpha and beta gains. Again, the beta has the three cases for the underdamped, critically damped, and overdamped. The difference is cosine 1 or hyperbolic cosine. Okay, timing error detector. The TED emits an error value proportional to the time difference between the optimal current symbol sampling time, which is shown in blue on this chart, and the actual current symbol sampling time, which is shown in red. So here you see off the left, we have a little bit of gap between the red and the blue sample, and the direction we want to go is we want to get closer to where that blue sample is, and that's shown here as a smaller timing error on the slide. Really, a TED is just an expression for the error value, E sub n. It's a formally derived equation, really. But to use these timing error detectors properly, you really have to pay attention to the assumptions in their derivation, which means going back and reading the literature about where it came from. The timing error detector can, in its computation, include things like the current symbol estimate, the nearby samples or nearby symbol estimates, the current symbol decision, the nearby symbol decisions, an estimate of the signal slope at the sampling time, or even the estimate of the energy per symbol over N0. In the end, they usually boil down to a simple expression. The Mueller, I hope I'm saying this right, the Mueller-Muller timing error detector equation is right there, where slice indicates a decision. A small signal maximum likelihood approximation timing error detector expression is there. It's simply the signal times the slope. Really pretty simple. A TED is characterized by something called its S-curve, which is its expectation of its error value out, giving a known timing error going in. And basically, the slope of the S-curve at tau equals a timing error equals 0 is what we'll refer to as the TED gain, which in the previous slides was marked as the phase detector gain. One thing to notice is that from these charts where the TED gain might be normalized, the actual loop implementation might have different units and you might need to scale things. This wonderful picture of the Garner TED, it's not really an S-curve, it's more of an S distribution. The actual S-curve is the expectation, which is the peak of the distribution running through the center there. You can see in an S shape. The S-curve shape and its central slope at timing offset of 0 depends on the TED's error estimator expression, the input signal amplitude, the pulse shaping filter or the pulse shape you're using, your input signal to noise, and some other factors. This means that this system really, if you don't condition your input and keep it sane, your TED gain is not going to be what you expect, and the system won't behave as you would expect it to. So really to find these TED gains, you have to sort of model the situation that you're dealing with in simulation in Octave, MATLAB, R, Python, whatever you use. Moving on to the interpolating resampler. Usually the symbol synchronization process reduces your sample rate, and your input samples shown here in red are not at the optimal symbol sampling time here, shown in blue. And we need to resample the input between the samples. And in this particular scenario, I show what quantity called the intersample interpolation fraction, mu. It's about 1/3 the way in between two samples. And so I'll move on. And I need to point out that this interpolator sample phase is actually a distinct quantity from the symbol clock phase. And I'm going to mention that right here and just leave it, but a lot of the GNURadio blocks that exist right now conflate these two quantities into the same thing and treat them the same, which causes them to not act as well as they should. The interpolating resampler is implemented with FIR filters. GNURadio uses fractional delay filters, either with an MMSE interpolator polyphase filter bank, or in the case of the PFB block, uses a match filter interpolator polyphase filter bank. Here's some words I don't know much about. Polynomial interpolation using Faro structure. GNURadio doesn't do this, so we don't use Lagrange polynomials or B-splines in a Faro structure to to do interpolation. Practical interpolation filters will impose a bandwidth constraint. The input signal really must be some fraction of your Nyquist or your sampling rate. That way you can get some bounded error on the interpolated output samples. So the ideal fractional delay interpolating filter is basically a frequency response of 1 modulated by a complex exponential to give you that shift in the time domain. And that complex exponential has a coefficient which is that, or has an argument that is that intersample interpolation fraction between 0 and 1. And a differentiating interpolator has an ideal frequency response of j omega modulated by a complex exponential to give it that time shift. So when we take the inverse discrete time Fourier transforms of these to get the ideal interpolation filter impulse responses, you can see for the interpolator filter we end up with a sync function, and for a differentiating interpolator we end up with something which basically boils down to the derivative of sync function. And you can see that mu argument in there. That's the fractional delay between samples. The problem with these ideal responses is that they're infinite. So what really GNURadio has done here is, instead of using infinite length sequences, they truncated to 8-tap filter lengths and ran some numerical algorithms to get a minimum mean squared error filters. So the GNURadio minimum mean squared error interpolator uses truncated versions of the ideal filters. It's really a bank of 129 filters. And there's one filter arm for every 1/28th of a sample that you want to interpolate between. This filter that GNURadio implemented only has minimum mean squared error frequency response in the range negative f sub s over 4 to f sub s over 4. So if we look down at the plot on the left, DC is on the left and Nyquist rate is on the right. And this is a plot of all 128 or 129 filter response frequency responses. And you can see from DC to f sub s over 4, it's 1.0 like you would expect. And then the filters all sort of start to diverge if you use bandwidth outside of that range. And the plot on the right is something similar. It's basically showing the squared error of all 128 filters, each plotted on top of each other. From 0 to f sub s over 4, you've got a nice response looking like at least negative 65 dB. But then as you start increasing, your error squared starts going up there. So if, just as an interesting plot, if you took GNURadio's minimum mean squared error interpolator and treated it as a polyphase filter bank and re-interleaved all the taps into a prototype polyphase filter, this is what you get, this blue line. And for comparison, I plotted a truncated sync on the green line underneath of it. So it's what we would expect. Okay, so going to the more practical aspects here, that was all our theoretical and book learning for tonight. The existing GNURadio blocks that implement this PLL architecture, there's 5 of them. The top 2 are float versions. The bottom 3 are complex versions. Clock recovery M&M, MSK clock timing recovery, and polyphase clock sync. I've added 2 new blocks, one for float and one for complex, that are called symbol sync blocks. These are a superset of all the functionality in those blocks on the left. And they fixed a lot of the bugs I encountered with these blocks. I don't want to dwell too much on the existing block's deficiencies, but I'll highlight 3 of them. The first one was I really just wanted tags to propagate properly through these things, and none of them did it right. And it turns out the reason they didn't do it right, because it was a really hard thing to get right. I spent a lot of time on that. The second big problem I saw with them, which maybe isn't numerically a big problem, but it affected how I had to decide to propagate tags and created an ambiguity, was that these blocks all conflated the symbol clock phase and the interpolator clock phase, which is only a valid thing to do if your input sample clock and your symbol clock are an exact integer relationship, which really you're never guaranteed that when you're receiving something from something with a different time source. This caused a little bit of self noise and effects like inability to stay locked on a clock pattern. from what I can tell. The other problem I want to highlight is not really a problem, it's just an issue. There was no way to change the TED, the slicer, or the resampler. If you wanted to do something different with a different timing error detector or a different resampler or a different slicer, you had to write a whole new block, bringing in whole new bugs, or in the case of copy and paste, you're just copying the old bugs and propagating them on. So the new symbol sync blocks are fixed replacement superset of the existing blocks. They can do everything all the other blocks could, except for in the case you can't change the match filter taps on the fly like you can with the polyphase clock sync block. If that's important to you, you might want to stay with that one for now. You have selectable TED, slicer, and resampler now. So I have not only all the TEDs that were in the existing blocks, I added a few more there. There's a pick list off to the left, lists them all. You now can change the TED slicer constellation. This matters for decision-directed TEDs, and it really matters for the complex M&M because it has an incorrect slicer in it, which isn't QPSK. It's something you wouldn't expect. The interpolating resampler, there are three options. One is the MMSE 8-tap FIR, which I had a little bit of discussion about. The third option on the list is the polyphase filter bank with the integrated match filter. That's what's currently implemented in the PFB clock sync block. And then there's one in the middle, which is a polyphase filter bank, really using the MMSE taps, except instead of using 128 steps, you can reduce it to 64 steps, 32 steps, 16 steps, in case you wanted to explore what happened there. It's probably not very useful, but there it is. Okay, so this was one of my first design drawings when I asked the pull request, and you don't have to pay attention to the drawing, but sort of the great thing about GNURadio core development is you get some expert advice for when you're using the wrong tools for the job. Now, Jonathan helped me pull this in from a out-of-tree module where I was fixing my frustrations, and he was. I got really good advice on the port, and he gave me a litany of things I needed to fix. The worst defense was I was polluting the API with all sorts of internal stuff that didn't need to be there. Something I didn't even realize, but if you have a pull request and something significant, the guys will work with you to make sure that it gets in an acceptable manner. There's still some work to do that he let me slide on, such as I really need help writing test cases for this because I don't know how to write the tests really well, and I don't have a lot of time either, but I guess who does? So let's see, moving on. So this is the actual cleaned up drawing of that design drawing you saw. This is the actual architecture of the new blocks. This is again, sort of a superset drawing. If you don't need a slicer constellation for your timing error detector, it's not used. If you don't need a derivative signal, the interpolating differentiator filter bank isn't used. If you're pulling in the matched filter into the filter bank, you don't need the one outside. The architecture, basically, the concept I had for this was I had a number of clocks to deal with to get all the effects that I wanted. There's an external clock for the input sample clock. We really don't have much control over. You have to deal with it. But then there's all the internal clocks to the block, which are all running synchronously. The interpolator output clock runs at the highest rate. And basically what drives that is you might have an output rate of 3 samples per symbol, but the TED might want 2 samples per symbol, so the least common multiple is 6 samples per symbol. So that interpolator might be actually internally running at 6 samples per symbol, but your output, it certainly isn't. There's the block output clock, the TED input clock, and the symbol clock, and the TED output runs at the symbol clock. You have the PI loop filter here. That's the one thing that you can't replace. But we don't actually do any phase wrapping and phase accumulation at the output of the PI loop filter. Instead, we just pluck off the instantaneous symbol clock estimate and the average symbol clock estimate and use that to control the resampling interpolator. Let's see, okay. So on the development side, now it's sort of easier to experiment with a new timing error detector. The recipe is, here are the files in the tree that you need to modify. Your new derived TED class only needs a simple constructor. and 2 methods to compute the error output term. 1 method for complex input, 1 method for float input. And then you can, if you don't need any new additional exotic inputs, you can leave the symbol sync blocks code alone. The tag handling, the slicer, the resampler, loop filter, it's all done. You don't have to touch it. You don't have to introduce bugs there. Adding a new resampler, same sort of process. Here are some files you need to change. You'll need 2 derived classes, one for floating input, one for complex input output. You'll need a constructor, a simple mtaps method, and then you'll need an interpolate method and a differentiate method. Leave the symbol sync blocks code alone, the tag handling, slicer, TED, loop filter, it's all done. Using a different slicer is something easier. You don't even have to modify the code. You can do this from the user space or user land. All you have to do is instantiate a custom constellation object, which would be needed only for the decision-directed TEDs, which currently are the M&M, the modified M&M, and the zero-crossing TEDs. You pass in the constellation object as the TED slicer. You leave the symbol sync blocks code alone again, tag handling, resampler, everything's all done. The idea here is code reuse. Let's not, the architecture for PLL clock sync is the same. Let's just change the things we want to experiment with. Okay. So I have a few slides here on how to take existing parameters from existing blocks into the new blocks. This one is the polyphase clock sync, which I'll slow down a little bit on. Obviously, the input type should map rather simply. Complex input output, the I/O type is complex. The timing error detector used by the polyphase clock sync block is one I call the signal times slope maximum likelihood TED. And let's see, samples per symbol translates straight through, timing loop bandwidth there straight through. Let me go down here. The polyphase and the interpolating resampler you want to pick is the polyphase filter bank match filter, and then you can just move your taps on over and your number of filters on over there. So that should be pretty straightforward. Again, I expect this to be reference documentation that you can look up later. Just as a test, I modified the MPSK tutorial, which uses the polyphase clock sync, and I added in the symbol sync block using the same sort of parameters. And I was quite happy to see that the polyphase clock sync blocks constellation is in blue, the symbol sync blocks constellation is in red, and I got slightly tighter clusters of points, so I was real happy with that. Might be just coincidence, though. Okay, the clock recovery M&M block that has complex I/O, the way you would map your old block parameters to the new block parameters is, I guess, the timing error detector. You want to use the modified Mueller and Muller, and you want to use the QPSK slicer. Samples for symbol translates right over. Your beta and your gain omega and gain mu, you're going to have to do some math based on the equations at the beginning of this presentation to get your damping factor and your normalized loop bandwidth. Quite honestly, though, it probably doesn't matter for this block because the constellation slicer it used was not QPSK. It was something weird. So even if you had working parameters with the old block, they probably aren't going to work well with the new block. And yeah, you'll use the MMSE 8-tap FIR filter. Something similar for the float version of the M&M clock recovery. I'll point out that this one uses the straight Mueller and Muller, not the modified one, and you'll be using the BPSK constellation for the slicer. Again, 8-tap MMSE FIR filter. The MSK timing recovery block. This one is used for CPM signals, basically MSK and GMSK. The I/O type is only complex. That makes sense. You use the De Andrea and Mengali generalized MSK timing error detector. You'll again have to go through some math to convert that alpha parameter to omega NT. And the error limit maps to the deviation by some simple algebra, which you can see on the slide. And the interpolating resampler is, again, the MMSE 8-tap. So going into some usage hints and gotchas, I'll start out with easy stuff. Your output samples per symbol can be anything in sort of a reasonable range of 1, 2, 3, 4, 5, 6. This is, I think, an improvement. although it might be a useless improvement over the existing blocks. Normally, you'd set this to 1 sample per symbol. If you had if you're upstream from an equalizer that wanted 2 samples per symbol on the input, then you'd set this to 2. And then if you want to do something more exotic, you can use one of those higher numbers. The maximum deviation is in units of samples per symbol. The smaller is better for acquiring the lock at the start of a burst. Too small and you'll miss data when the symbol clock that you receive is far from the expected nominal. The tracking resets on this block on the time est tag, or a new tag interpretation I have is clock est, where the time est says at this sample plus some small offset is where someone thought the optimal symbol sampling point was. The clock est tag has two parameters. The first one is that same sort of thing. At this symbol plus some small offset is where you should reset your timing. And then the clock est tag also, if you can provide a estimate of the sample clock period from what you've done open loop, it will also kickstart the synchronization process. So these are open loop hints that you can provide to these blocks, and it will react to them. Okay, something that's probably neglected when people use these blocks is that the input signal conditioning and filtering. The MSK signals and the MSK TEDs don't use match filters because of the CPM nature of the signal. It's not really pulsed there. But a narrow IF filter can be beneficial. Your input signal in general should be at a consistent amplitude. I'll just suggest plus or minus 1 as the extents, which means out front you'll need some AGC. The timing error detectors have specific assumptions about your input amplitudes, and you shouldn't ignore those. Otherwise, you'll get results which will be suboptimal. The input signal amplitude for decision-directed TEDs should really match your constellation. Again, these TEDs really are expecting that. One GNURadio quirk that's going to bite some people is probably that GNURadio's constellation object will silently scale your constellation so that the average magnitude of the constellation is 1.0. For QPSK and BPSK, it doesn't matter. The radius from the origin is the same, and the magnitude will stay at 1.0. But if you put in a constellation with a large spread of points, GNURadio is going to scale it on you, and that's going to trip you up, so be careful. The input signal should normally be non-return to 0 with no DC offset. The input signal should be peaked at the symbol centers, except for the MSK signals, obviously. This is normally accomplished with the match filter. So the Synch block's PFB match filter option for the resampler can do the match filtering for you. The exception would be if you have a rectangular pulse filter and a timing error detector that needs a derivative. It kind of breaks down there, and you'll have to use an external match filter. So loop parameters and tuning. You're going to need to use simulation to determine the TED gain. Otherwise, you can't know what damping regime you're in, whether you're underdamped or overdamped or critically damped. And you need to make sure that the TED gain is scaled to the proper units for the loop. Am I running out of time? I'm sorry. And OK, I'll just cut it there. Just a pretty picture about some diagnostic outputs where we can see that there's intentionally bad tuning will give you a clock estimate that goes all over the place until it settles down. I'm doing a tutorial tomorrow where I'll go demo some of this stuff and hopefully clear anything up if I confused anyone. All right?
OK. Well, we have time for 2 questions. So
yeah. No, thank you. The question.
So Phil has a question. Anyone else? We can start. All right. OK, we'll start with Phil,
no.
and then we'll.
Yeah.
What were your biggest issues with the tag propagation?
The tag propagation, basically the blocks, these blocks are variable rate. And even if you tried to use the scheduler magic to try and sort of match it, it was only the runtime would only give you an approximate propagation of the tag, and the error would accumulate after a while. So I was using these things. I had an energy detector up front to mark a start of burst, end of burst. I'd send it to the clock recovery, and the tags would slide because when these things are free running on noise, their decimation rate really just varies all over the place, and the scheduler can't really do that. The block itself has to be the one doing the tag propagation. the implementation to get it right will actually, if it gets to a point where it can't figure out because it's running short on input samples where to put the next tags, it will actually backtrack one, return to the scheduler, and wait for more input. So that was sort of if you look at the work function, it gets really hairy because occasionally there's lots of places, not lots of places, a few places where it makes the decision, I have to backtrack, right? Next question.
Fred Harris?
Okay, you don't want me to stand up, but I did anyway. One of the things that you don't see in the literature, and you only find out the hard way, the M&M time and recovery loop won't work if there's significant distortion in the channel. It requires the zero crossings of the sine x over x to be present. If there's distortion, they disappear and the loop won't lock. The reason I know, we once built a bunch of radios and sent them to Japan, and in the canyons of Tokyo, they failed to operate. You had to bring all the radios back and replace the M&M. I will never use it again for any modem I ever build.
Right.
So if you're interested, I can show you what I think the right ones are, and we can fix that if you'd like.
Sure, and if we have, and I'd like to talk with you about that, and also if there's other timing error detectors you want to experiment with, we can add them to this easily, and they can, people can do comparison tests. The M&M, I personally don't like myself. It doesn't work that well.
That's right.
In my experience.
Right. Okay. You should know that. Okay.
Tom Rondeau?
Yeah. So first, Andy, this is fantastic work. It's probably some of the best work we've seen, mathematical work that we've seen for a long time in GNURadio. So that's like awesome right there. So it's like the exact thing that we want to see happening, but then there's also like, we also don't want to see some of what's happening because when I first introduced a lot of that new work there, I think it was years that I was the only one able to use those blocks effectively. No matter how well I thought I wrote the documentation, it all came back to, Tom, how do you do this? And I would give you the right parameters. And you've actually just exploded that like combinatorial space. The fact
You're welcome.
Yeah. and I know you know that I worked a lot on the blog to try to expose how we actually do that. And this presentation is again fantastic as a resource for us to use to do that. We still have to work somehow, and I think this is a community challenge. How do we translate that mathematical theory and thought process to make this usable to normal users of GNURadio, to bring in ideas like what Fred just said, to allow us to understand how these things impact our choices and how we parameterize these things?
Right. And I've provided a little bit of an example. I've provided example flow graphs, which aren't that exciting. And I did provide one example script in Octave for simulating the M&M TED and Gardner TED for the specific input situation of that one example flow graph, which really relied on my expert knowledge. And I'm not quite sure how to boil that down into really a general algorithm just yet on how can someone simulate an S-curve for their given situation, right?
I totally understood, and it's a lot of work that we have left to do to be able to translate those things to the rest of us. Yeah, so great.
Okay, I see no more hands. I think if we could sort of summarize that conversation that the two of you just had, it's that no matter how easy we make SDR, it'll always be hard because it's just hard. Radio is not it's just not that easy, and all we can do is is the best we can do to try and document and make it more accessible. And I think I think you also have examples, right? Like as part of this.
There were two example flow graphs checked in, one for complex, one for float. The complex one is really sort of embarrassing because it just takes the same information, puts it on both the I and Q channel, so it's really not that exciting. But
I have a hunch that people who will be using single carrier stuff will just work off of those examples, and that's totally fine. I think that's great. Okay, well, that's it for the day. We have nothing on tonight, so we'll see each other tomorrow morning. Thank you very much for showing up, and I'd like to one last round of applause for all the speakers of the day.